Now we're ready to go to the third example. This third example is a bit more complex. An archer wants to shoot an arrow through an apple which is suspended by a string tied to the branch of a tree as shown in the diagram. The apple is 3.5 meters above the ground and a horizontal distance of 35 meters from the archer. The archer's bow is 2 meters above the ground, aimed at an angle of 24 degrees above the horizontal. At what speed should the archer shoot the arrow? Now let me comment that this is kind of a strange problem because archers don't generally control the speed at which their arrows leave their bows. But that's the way the problem's written, so we're going to deal with the way that it is. Let's start by putting the origin of our coordinate system where the action begins. And we can then write things in terms of horizontal and vertical parts. Since the archer aims his arrow upward, then I'm going to suggest that we call up the positive direction for the vertical. And since he's aiming the arrow to the right, then I would say let's call to the right positive for the horizontal. What that means is that vertically the acceleration is going to be negative 10 meters per second squared, and the position where the apple is plus 35 meters. Now they tell me the arrow leaves above the ground at 2 meters, and the apple is 3.5 meters above the ground. So I'm going to say the y position where the apple is relative to my origin is going to be 1.5 meters. I think that's relatively easy to see from this diagram. Now I'm trying to figure out what V0 is. In other words, what is the numerical value for the speed? I know what the angle is, it's 24 degrees, but I don't know what the speed is. I can write an expression for V0x and V0y in terms of V0 and 24 degrees, even though I don't know what the hypotenuse of that initial velocity triangle is. Let me sketch a triangle here to show you what I mean. I'm looking for the hypotenuse of that initial velocity triangle. I don't know the horizontal and the vertical legs, but I know that whatever those horizontal and vertical legs are, they are related to the hypotenuse through a sine and the cosine. I'm going to go ahead and write that piece of information down in my horizontal and vertical lists. Now, what ties these things together is the time. I could figure out the amount of time or an expression for the amount of time that it takes for the arrow to travel vertically and an expression for the time that it takes the arrow to travel horizontally. Then I would have two equations and I might have two unknowns. The two unknowns are going to end up being the initial velocity V0 and the time. Mr. Haynes, how would I know that if I've never solved problems like this before? The answer is that you don't. You just have to play around with it. What the purpose of these problems is to give you some practice, and I'm trying to show you what it is that you can do to try to simplify or to try to cut to the chase on some of these problems. Because there's a whole mess of stuff that you could look for. I'm saying go for the time. 9 times out of 10 in projectile motion problems, the time is going to be an important variable to have an expression for or a number for. And so 9 times out of 10, if you can figure out how much time happens between when one thing occurs and when another thing occurs that you're interested in the problem, then that is going to help you solve the problem. So let's go for the time. Let's figure out horizontally an expression that involves the time. And I'll use the second equation of motion to help me. Let me put in my zeros. X0 is 0. Acceleration in the x direction is 0. So I can rewrite this equation in simplified form. And I'm going to go ahead and make this substitution for what V0x is in terms of V0 and the angle. Now, let's look at the y equation. There's a 0 I could insert into that. And I want to write V0y in terms of V0 and the sine of 24 degrees. So I can rewrite my y equation to look like this. And now I claim to have it because I've got two equations and two unknowns. I've got an equation in x and I've got an equation in y. Now they're not easy equations. I claim that I can substitute one equation in for the other and solve that equation for V0. I could solve the x equation for t and substitute that into the y equation. It will be an ugly looking equation, but I can do it. Or I could pull out my handy TI-89 calculator and use TI solve to figure these things out. I'm going to do it both ways and try to illustrate it. Here we go. Solving the x equation for t, I get this. And now I could feed this expression for t into the y equation. I'm going to need some space, so let's do it. There's my substitution, and I've got some things that are going to simplify. For instance, this v naught upstairs here and this v naught downstairs there are going to cancel each other. And I can write sine of 24 over cosine of 24 as the tangent of 24. Now I'm trying to figure out what v naught is. I see my v naught is buried down in the denominator of this second term on the right hand side. So I'm going to subtract the x tangent 24 from both sides and then massage this equation to get this v naught on one side and everything else on the other side. Now if I look the left hand side as a term in parentheses, I could divide both sides of the equation by the parentheses, multiply both sides by v naught squared, and take the square root. I want to do that all in one step. And now I know all these things on the right hand side, and so I can substitute them in and solve that equation for v naught. What an awful looking expression. And it looks kind of hopeless right now because I got a negative sign upstairs with that 10 meters per second squared. But let me point out that on the second parentheses downstairs, that's going to turn out to be a negative sign. Those negative signs are going to cancel, and I'm going to be okay. Let me put in the numbers. And I get that v naught is equal to just under 23 meters per second. That's algebraically. But I can go back up to my x and y equations and use TI solve to help me solve these. So I want to rewrite these equations down on this next page and then pull out my TI-89 calculator. So let me rewrite the equations. Now let me put in the numbers. And I can simplify the y equation even more by taking this 1/2 and multiplying it by the negative 10. I have two equations and two unknowns. Now let me pull out my TI calculator. And here we go. Let's solve these two equations for the initial velocity. And I could also figure out what the time is, but I'm really interested in the initial velocity. So I'm going to solve the first equation. 35 equals v naught. I'm going to use the variable z to represent v naught because I've got x and y already in other equations. I don't want to confuse them. Times the cosine of 24 multiplied by t. And I want to solve that equation for the time. There I've got an expression for what t is in terms of v naught. Now I want to solve the second equation. So I'm going to put it in 1.5 equals v naught, which is the variable z, times the sine of 24 degrees times the time minus 5 times the time squared. I want to solve that now for the initial velocity, z, with all this other stuff up there. And now when I put in the numbers, I get z, or v naught, is equal to plus 22.8 or minus 22.8. And it turns out that the number I want is the positive number. There is my solution. So you can solve that problem algebraically, or you can solve that problem with TI solve. That's it.